Welcome everyone. Today we have Mario Martínez presenting his work entitled Extending the Learning Using Privileged Information Paradigm to Logistic Regression. So Mario,
thank you. Thank you for the introduction. Hello, my name is Mario. I am a PhD student at BCAM, and I'm going to present one of our recent works, Extending the Learning Using Privileged Information Paradigm to Logistic Regression. The work is developed with the help of Susana, Lasai, Iñaki, and José Antonio Lozano. The talk is divided into the following parts: motivation of the proposed work, some preliminaries, the development of the classifier, results, the discussion, a brief conclusion. We move to the motivation of the proposed work. As we have seen in the title, we have the privileged information here. So what is the privileged information? It's really simple, the concept. Privileged information are features available at training time, but they are not available at prediction time. So here in the training stage, we have the regular features, the privileged features, and our output for training the model. But in the prediction stage, only with regular features, we are going to obtain our predicted output. Okay, and this paradigm is called the learning using privileged information, LUPI. And why can privileged information be useful? Because models learned with privileged information can outperform models learned with exclusively regular features. Our motivation here to use the privileged information is because we notice of the presence of this type of privileged features in some clinical dataset. Here we have an example of the prognosis of a random disease. The data that we collect here are, for example, some blood tests, temperature, heart rate, symptoms, and comorbidities before the admission of the patient. And our output here is the 20-day survival, if the patient is going to die or if he's going to survive. So in that traditional supervised learning classification, we have these inputs and this output for training the models, and with this, in the prediction stage, with these inputs, we can predict if the patient is going to survive or if going to death. But here, after admission and before the output is known, it is possible to have more information about the patient, which is known as privileged information. Our objective is to harness this information with the LUPI paradigm, and in this case, the privileged features that we could have are collected during the hospital stage, and these type of features are known for the patient who have already suffered the disease and were admitted to the hospital, but are unknown for incoming patient. We don't know this information for incoming patient. So the main point here is that privileged information influences the learning process of our models, but in the prediction stage, the prediction stage is the same as in a supervised learning classification. With the inputs before admission, we obtain our predicted output. Our proposal is to merge the logistic regression, which is widely used in the clinical field, with the learning using privileged information. And we have developed two new novel methods, the LRIT Plus and the LR Plus. So we move to the preliminaries. I'm going to say some things that are important for the following slides. First of all, the notation. For a classical supervised classification, we have this set of data with n number of instances. Here, xi means the different values of the regular features that we have, and yi are our binary output. And when we are going to denote the privileged features, we use an asterisk here, and here we have the regular features, our privileged features, and our output. And in some cases, we need to denote regular and privileged features together. So in this case, we use an apostrophe, and we collect the regular features and all the values of the privileged features here. So also as a quick reminder, I think that we all know this equation. We have the posterior probability of the conventional logistic regression, that here the parameters, we have the parameters omega and beta that are really important for our model. Well, we move onto the development of the classifiers. It's important here to explain two different models before explaining our method. I'm going to start with this one. This is the base logistic regression, which is the traditional logistic regression learned with only regular features. It's a classical supervised model. And here we have the unreal privileged logistic regression, which is learned with regular features and privileged features. But here the privileged features are treated as regular. So this model is unreal. It can be implemented in the real world because we are using privileged feature, or we are treating privileged feature as regular features. It's like an upper bound. And obviously, privileged features commonly offer relevant information to the outcome. So LRUP, or the unreal privilege model, should outperform this base classifier. Our objective here is to propose a privileged model which is with inputs as regular features, and it is influenced by privileged features that could overcome the base classifier. And we are going to, theoretically, this model is going to be placed between the unreal privilege model and the base classifier. And here, the key idea for the computation of our model is to obtain that our privilege model produce output as close as possible to the unreal privilege classifier. If we traduce this to an equation, we have this, that our objective is to obtain the optimal parameters that minimize some distance that we are going to define in the following slide between our privilege model and this unreal privilege classifier. Here we have a figure that in this rectangle means that we contains all the parameter space with the regular and associated with parameters with the regular and privileged features. The L denote the regular features, L asterisk the privileged features, plus 1, which is the intercept. Okay, and here this set of parameters only represent the parameters associated with the regular features. So in this set, we have inside only the parameters of the classifier and also the parameters of our privilege model. But here outside, we have the parameters of the real privilege classifier because this model is composed of regular and also privileged features. A useful notation for the understanding of our model is the projection. Our objective here is to project this unreal privilege model, which is learned in a larger parameter space, we consider regular and privileged features, onto a lower parameter space where only we consider the regular features. That's the main idea and the main point of our method. So our distance d is going to be a convex function, and we choose two square functions. One of them is governed by logits, and the other by posterior probabilities. These are our two methods that we have proposed. For example, here for the LRT, the optimal parameters are computed according to minimizing the distance between the logits of our proposed LRT and the logits of our unreal privilege classifier. We want to minimize this distance between the logits in order to infer the optimal parameters of the logit model. Okay, and for the posterior probability model, is more or less the same. We maintain the same structure, but instead of using the logit structure, we use the posterior probability. And here we have this will be the posterior probability of our model. We are going to minimize this omega and beta, and here we have the posterior probabilities of the unreal privilege classifier. Well, once we know how our models work, we move on to the results. I'm going to compare the different performances of the classifier on different datasets, on MNIST Plus, and some youth datasets that we all know that are very common. First of all, this MNIST Plus dataset is commonly used in the loop paradigm, and it's based on the traditional MNIST dataset, but with the difference that we only collect the number 5 and 8. And as regular features, we have the pixel of these images of the number 5 and 8. Our output is we are going to take an 5 or an 8. And privileged features we have are these privileged features are extracted from a poetic description of this number, and from this test the author that is a bit crazy, obtained 21 privileged features, okay? So our training set contains a total of 100 samples, and from 40 up to 90 samples are randomly chosen for training the model. And here we can see the evolution of the accuracy for when the training data size increase. The red line represents the base classifier, the blue line the LR plus, and the orange line the LRIT plus. Here we can see how the LR plus outperform the base classifier for every training data set, and the LRIT plus outperform the base classifier when we have low training data size, which for larger training data size we obtain similar results as the base classifier. And despite the fact that the privilege information can appear in different scenarios, there are not a lot of benchmark data set that directly point these privilege features. So for that reason, we use this UC dataset, the breast cancer, the obesity, and the wine dataset. But here we have a problem because the privilege features are not pre-specified in this dataset. So those features, we need to specify these privilege features in order to be able to apply to implement our model in this dataset. So those features with large parameter values within LRI blue are treated as privilege. Here we have an example. I trained the LRUP model for the wine dataset. These are the features of the models and the parameter values associated to each one of the features. And I'm going to consider from 1 up to 4 privilege features. And for example, when we consider 2 privilege features, I'm going to treat as privilege the first 2 privilege, the first 2 parameter values that I have here, and the remaining are going to be treated as regular features. So I'm going to obtain the performance of the different classifier for 1 privilege feature, for 2 privilege features, for 3, and for 4 privilege features with the different dataset that I have here. And here we can see the evolution of the accuracy over different number of privilege features for the breast cancer dataset, for obesity, and for wine dataset. For breast cancer dataset, we can, well, here we have the red line is the same as the MNIPS Plus dataset, the base classifier. The green line, the unreal privilege classifier that is new. The orange line, the LRIT Plus, and the blue line, the LR Plus. And for breast cancer dataset, as we can see here, our model outperformed the base classifier. For obesity datasets, only the LR Plus outperformed the base classifier. And for wine dataset, we obtain similar performances between our models, LRIT Plus and LR Plus. And here we can see that for low number of privilege features, the distance between the base classifier and our privilege model are larger than for 3 or 4 privilege features. Well, in this graph, we can see a comparison of the parameter values for the breast cancer dataset when we consider 2 privilege features. So we are in this point, exactly in this point, we are going to compare the parameter values of these 4 models when we consider 2 privilege features for the breast cancer dataset. And here we can see all the features of the breast cancer dataset. And in these 2 are the privilege features that we have considered. That you can see that they only appear for the unreal privilege classifier. Okay. And here we can see that the LRIT Plus acquire larger values for example, for average perimeter and average radius, and the LR plus acquire larger values for worse area, or for example here the concavity perimeter. I think that is that feature. To sum up, here we can see how the influence of these privileged features affect to our methods, to our models. Finally, we move to the discussion. Here, despite the competitive performance of the proposed methods that we have seen, marginal improvement or worse results with respect to the base classifier are in a small number of cases obtained. So, prior to the learning processes of our approaches, can we determine if the privileged features will have a positive effect on our approaches? So, if our LRIT plus or LR plus can outperform the base classifier? Yes, a metric associated with the LR plus classifier is provided. But before explaining this metric, I'm going to explain something that are really important. As quick reminder, as we have seen in the previous slide, LR plus intends to replicate the probabilistic output of the unreal privilege classifier. So we obtain that LR plus outputs the identical class label as the unreal privilege classifier when the following inequality is satisfied. Here we can see the posterior probability of the unreal privilege classifier, here and here, and this is the posterior probability of the LR plus. So this inequality states that the more extreme the probabilities of the unreal privilege classifier, the more extreme these probabilities, the easier is for the LR plus to output the same class label as the unreal privilege classifier. So here we can see that we have to take in mind that the more extreme the class probability of the unreal privilege classifier, the easier it is for LR plus to mimic the unreal privilege classifier output and consequently outperform the base classifier. So if we translate this into a metric, we have the mean predicted class probability for the unreal privilege classifier. Where you can see here this is the probability of the unreal privilege classifier, here and here, and it has a range between 0.1 and interpretation is larger, the more robust is the classification for the LRUP model that can influence how our LR plus can perform. And high MPP score means that predicted sample outputs statistical probabilities, and low MPP score means that predicted sample outputs extreme class probabilities. Finally, here we have evaluated this MPP over 10 different data sets, and also we check if our LR plus outperform or not the base classifier. We can see the high MPP values means that our LR plus can meet the LRUP performance and generally leads to overcome the base classifier. But for low MPP score, we don't obtain consistent conclusion because, for example, here for the Avalon, we obtain an MPP that is lower than the white matter, and we have a good behavior of our LR plus. But for the white matter, this MPP is larger, but the behavior of LR plus is worse, can outperform the base classifier. So as conclusion here, only with high MPP score we can reliably determine the positive impact of privileged features on the LR plus classifier prior to its learning. Finally, the conclusion. Well, we managed to expand this logistic regression to another a novel paradigm, which is the privileged information. And we also, with this projection-based framework that I have explained, it can be adapted and transferred to other algorithms. We propose a novel, a reliable metric, the MPP, to determine beforehand the impact of privileged features on LR+. And I want to remark the usability of this model. Thank you very much, and that's all.
Thank you, Mario, for your talk. Now we have some time for questions, so anyone? No question?
Hi, thank you for your talk. It's a very interesting topic, and I was thinking, well, just a couple of questions. First, what kind of scenarios are interesting? I think that in general, for looking for places where this is interesting, there are some kind of, say, forensic scenarios where you, after something happens, it's similar to your problem so maybe in that sense, any kind of related with that, I think that you could find interesting places where you can apply. And the other one has to do with this last thing that you've said, and it's more instead of have you thought about sort of measuring the utility of privileged variables, not the whole data set, but just individually? Because in these scenarios, forensic scenarios, you may have a very extensive analysis after something happens, and probably only a few of those variables are interesting. Instead of introducing all of them as privilege, it would be interesting to have a way to measure the utility of each variable individually. Sort of feature selection, but privilege info.
Yes. Yes, here in the presentation, I don't put all the experiment that we have carried out, but we have a conclusion here that is that with a small number of privileged features, usually our models work better than with a larger number of privileged features. So it's really important what you have said. It's important to select the correct privileged features in order that our model can outperform this base classifier that we have here.
And have you thought about metrics for that, just to selecting which ones?
It could be a good idea, yes.
And also just a question, about because you're working in regression or it's classification.
Classification.
Okay. Is there anything for regression? Have you checked privilege information for regression?
The original authors propose the SBM, which is the classical paradigm, the privilege information paradigm, is originally developed in the SBM, and he proposed a regression with the SBM.
Oh, it is for regression. Okay. And any other algorithm or something? Because I checked this privilege information many years ago when they published the first paper, and I do not have any information about algorithms or how many, just more or less, how many proposals.
There are a few papers about privilege information. I have seen some papers with some neural networks that consider this privilege information, convolutional neural network also, and the AdaBoost has a version with privilege information, and yes, but there are a few papers about this topic.
Okay, thank you.
Well, it's a question similar to Borja's. Is related. Is there any way that, I mean, I agree with what Borja says, that you had some way to distinguish or to select among these variables that would be useful. But is it possible in this scenario that you may get one of this type of privileged variables that is actually explained by the original variables, that you could predict, that is redundant, let's say in a different way, that is it possible that you could filter them in according to the extent that they are predicted by your original variables?
It could be an option, and the original author also proposed a paradigm that with the regular features they can obtain these privileged features, and they use these privileged features that are not real to in the model. And but yes.
Okay, and then related also to that question, I don't know, with logistic regression, you are not able to model interactions between variables, right? Between features.
No.
You are not. So it might be the case that in some cases, with your original variables, you would be able to get a better prediction without additional privileged information just by modeling interactions, right?
Right.
Okay. So,
right.
So are you considering using more sophisticated models that model interactions? Something else apart from logistic regression?
It could be a notion. What we are considering, that I think that it is not the same as you are thinking. It's just, for example, here that we are using a probability. This is a probability. Saying this probability of the logistic regression that we have obtained with the probability of another more robust model, like it could be an XGBoost or a neural network, that a probabilistic model instead of this logistic regression of the unreal privilege classifier.
Okay. Thank you.
Just a clarification. I mean, we are using a logistic regression because we started with a problem in the health environment, in the health scenario. So physicians, they love logistic regression because they think they can understand it. But of course, I mean, it could be extended to another model where you consider interaction between the variables, but of course it would be much more difficult. So our first approach would be, first of all, to try to consider the model that is learned with all the features, to consider more complex models. And then, because I mean, the formulas, the good point is that the optimization problems continue being convex. So it doesn't matter what you put on the right, the optimization problem continue being convex. So that's one way to follow. To translate, I mean, of course it can be translated to more complex models, but it's more complex.
I was also thinking that maybe using more complex model is not guaranteed to have a convex expression that can be optimized. We don't have, who knows, no?
Yes.
Who knows? No,
but we use a
we were lucky.
probabilistic model here is only change this number with other number of a probabilistic model. So so it's going to be complex.
Okay.
Because this unreal privilege model is learned before we compute this formula that we have here.